The final, as you know, 3106 Echeverry from 8 to 11 a.m. on May 12th. That's a Thursday. So you also know the drill. Bring paper and, bring pens, pencils, calculators especially, and bring a cheat sheet for yourself. You can bring what you had before for the other two midterms. And you can now add another sheet, and on one side of that sheet, put whatever you want of astronature, and on the other side, put non-astronature stuff. All right. So any questions about the final? Yes?
Is it going to be more focused towards the end of the class?
Yeah, it's worth mentioning. I've said it a couple times already, but yes, it's going to be biased towards the last one-third of the class, but we will be drawing from many concepts that we introduced throughout the course. But, if you are pressed for time and you did well in your first two midterms and you understand that material, by all means, be studying that last third of the class, right? The last two problem sets in particular are things that we love testing on. That kind of stuff. And then in terms of practice problems, we'll be giving those out to you guys sort of Monday or Tuesday, and we probably won't have the solutions out in time for the review because we really want the review to be about the review and not about going over those problems. So the GSIs and I will make ourselves available on a number of occasions with office hours, and we'll announce what those office hours are going to be next week. But expect that I'll have an office hour sort of early next week, and then also the following week during the finals time, but obviously before the final. So that might be a good time, like after we hand out the solutions, if you still have questions about what's in those solutions, ask us what's going on. But the review section will be a broad overview of the entire course given by the GSIs, and obviously come armed with questions, and they'll try to get to those. Any other questions? Oh, yeah, so you know that if you do what the GSIs and I deem an acceptable job on your extra credit project, you'll be given a point or two on your final grade. That is, we're going to calculate sort of the distribution of the letter grades by doing all our scalings and all that stuff numerically. And then after that, we'll add in the extra credit point or two, and then it may bump you into another category. So essentially, the curve is going to be generated without the extra credit points, and then if you do extra credit, we're going to add that in. So we're going to have some sort of bias up to higher letter grades or lower in the alphabet. And is that right? Yeah. I'm thinking about the cosmic background radiation and Sunyaev-Siltovich effect. I'll make that joke later. Just remind me to make the joke. But those that do like a really great job, and in fact, the GS and I like to get together and we'll talk about each one of these, and we'll say which one is the best. The best one wins a prize. Not only will they get 4 points on their extra credit total, but they also get an autographed book by me. This book just came out last month, and I would love it if you guys would read it. And you could buy it, I guess, for your summer vacation. But somebody won't have to buy it if they do extra credit. They do a great job. And then I'll sign it and say whatever you want, like you're the best student ever or something. You could give it to your parents and they'll freak out. All right. So, and I should say also that there's a colloquium today talking about the origin of spiral structure in galaxies. That's at 4 p.m. Lars Hernquist. And then tomorrow, also at 4 p.m., not number 1 LeConte where the astro colloquium is, but number 2 LeConte where the physics colloquia are. That is going to be given by a string theorist on the end of space-time, and I still don't understand what that means. All right, so last time we talked about standard rulers. We introduced the idea of an angular diameter, and we said the angular diameter distance had to be determined or defined by the fact that dA times the angle that you observe some source on the sky has to be equal to L. Okay? So if we have something that's like 10 kiloparsecs on the side, it's a standard ruler somehow, we're going to see at sub 10 some amount of angle theta on the sky. This equation has to be satisfied. And we saw that there's a relationship between dA, dL, and d proper, and they're just different by 1 plus z squared. So dA is equal to dL divided by 1 plus z squared, and it's also equal to d proper divided by 1 plus z. In terms of the standard ruler, we saw that the cosmic background radiation, and we talked a lot about its origin, its physical origin. You worked out a problem set on this to come up with when reionization happens. We talked about there being perturbations left over after the Big Bang that would leave an imprint on the cosmic background radiation. In particular, what we observe are hot spots, and those hot spots have some sort of delta T, so slightly different temperatures relative to the average. The average is a very, very good approximation of what the total temperature is of the cosmic background radiation today. But when we look off in some spots at 1 part or a few part in 10 to the minus 5, we see slightly higher values, right, of order hundreds of microkelvin relative to a background of TCMB of a few Kelvin, okay? Right. So any questions about that? I'm going to get into the origin of structure in the context of these perturbations, and then we'll talk about where these perturbations came from. But I want to just sort of finish up with a discussion about other standard rulers. The idea here is that if in a standard ruler, and this is the so-called Sunyaev-Zildovich effect, or I'll just say the SZ effect. The idea here is that you are making an observation of a cluster of galaxies, and you can infer some typical size on the sky of that, right? So there's going to be some angular size of this on the sky, call it theta, and you are interested in knowing what this size L is. And it's usually called LT because it's a transverse size. And it turns out that there's a way, a fairly clever way, of coming up with a measurement or an inference of what we might call the radial size. And that is basically an inference of the total size in the direction of photons heading towards you. What you do is you look at the cosmic background radiation, and you look at this cluster through the CMB. Now, this cluster has hot gas in it, which means that it has free electrons. And these free electrons, as a cosmic background photon, are traveling through this hot cluster of gas. These free electrons will every now and then interact with these photons and preferentially wind up changing their effective energy as they wind up leaving this system, right? There's effectively an optical depth. And that optical depth will be something that's important. And I'll show you some of the mathematics of that when I show it on the screen in a minute. But the point is, by using the temperature of the hot gas, how might we measure that again? Emission spectrum, yeah. And what kind of emission are we expecting again? Bremsstrahlin radiation. So we get a spectrum of this, say, with an X-ray telescope, the Chandra X-ray telescope, for instance. We get a temperature of that hot gas. We get a total luminosity of that hot gas. We don't actually get that, right? What do we get? We get a flux of the hot gas. And we also infer a luminosity distance, or we assume a luminosity distance. We might need to know the redshift of that cluster. And what do we get from this? Well, we get the mass of, the virial mass of the cluster. That's good. But we also wind up getting the total number density. The number density of electrons that the average photon would have to travel through on its way to us. We then make a measurement of the overall decrement of the CMB light, because you wind up seeing in a second that some parts of the spectrum are decreased in its brightness and some part are increased. And using that, we get a measurement of, or an inference of LR. And by comparison of LR divided by LT, this is how we wind up getting our angular diameter distance. There's a number of steps that you have to crank through to get to this point, but I wanted you to just see that what we observe is hot gas, and we get its luminosity, we know its redshift, and we can sort of turn the crank and figure out what the mass of that cluster is, which is pretty interesting. And likewise, we can figure out the angular diameter distance of that cluster. All right, so this is a bit complicated, but let me just sort of step you through it. On the left-hand side, you see X-ray images. So these are essentially taking the Chandra X-ray telescope and looking at X-ray clusters, and reconstructed distributions of the temperature as a function of position. And this is position in Archimedes or something. So this is sort of a model for the cluster. First of all, what do you notice right away about those models, given the fact that we're making some inference about that LR and LT are going to be equal to each other? They're not spherical. So right away, we see that clusters, which we call relaxed and virialized, are not perfectly spherical. You know that, right? There are no sort of perfect spheres, other than a black hole and almost a neutron star. But on large scales, that's not true. So this sort of requirement that LR is equal to LT for us to make this inference, as we'll see, turns out to be incorrect. Okay, so here's what we see as the cosmic background radiation. That's in the dashed line, and this is as a function of frequency. And what kind of curve is this again, that dashed line? It's a black body. But what you notice is that some of these photons basically all the photons wind up getting boosted to higher energies. So if we observe basically to the left or lower frequencies than, say, something about 220 gigahertz, then should the cosmic background in that part of the sky be brighter or fainter? William?
Brighter?
Why?
Because they're... Oh, wait. I'm not sure.
Look at the this is the observed spectrum, right? And so this is some measure of intensity.
Oh, yeah. To the right, it should be brighter.
Yep.
Because it's shifted up. Sort of.
And there's also, you're right, so to the right, all the photons are moving over. To the right, you should have a brighter cosmic background, effectively, and on the left, you should have a fainter one. And interestingly, you have some sort of null point where you don't expect that temperature or that intensity to change, which is kind of neat. So that's obviously what's observed. Here is a 3-band image of a part of the microwave background looking towards a very massive cluster at a reasonably high redshift. And you see a big hole in the cosmic background radiation. Right? It's not that that part of the sky never made any structure. In fact, there's plenty of cosmic background behind that. It just, all that light winds up disappearing because you have these hot electrons, which are what are called Compton boosting these photons to higher energies preferentially. Not by a lot, but by enough to make it matter. And look, this image on the right-hand side is taken at 220 gigahertz, which is approximately this null point. Right here. So this change in the temperature, because you can, in the context of radio astronomy, you can think about the change of this intensity as effectively a change in a temperature. This change in the effective temperature, if you like, the intensity, is going to be proportional to the integral of the line of sight, through the line of sight, of the temperature of the X-ray gas, T hot gas, or Tx up there, and the number density that we wind up inferring. And so we have something that we can measure on the left-hand side from our observations of the cosmic background radiation, and something on the right that we can infer from our X-ray measurements. And then also we need to get a redshift. And combining all of those things and making that inference that LR is equal to LT, we can get a measurement of the angular diameter distance out to different redshifts. This is a very, very hard measurement, as you can imagine, right? This isn't just, oh, I'm going to take an image of a supernova, and, oh, it's too faint or it's too bright, cosmology, boom, right? This is, you have to use, you have to do observations at microwave wave bands. You have to do observations at X-ray wave bands. You have to do a lot of modeling. You have to get an optical spectrum of the cluster to figure out what redshift it's at. This is highly non-trivial, but it's interesting because this equation that we have here on the left-hand side, the right-hand side, is something that is really local physics. It means that I have a way of constructing a sort of a standard ruler in space using local physics that I can infer by my observations being very far away. So I can construct a standard ruler up there. And when you can construct a standard ruler and then you can observe the actual size on the sky, then you have a way of making cosmological measurements. Yes?
What were the units of that intensity?
This is million Janskis per steradian.
Okay. I don't remember what a Jansky is.
A Jansky is a lot of energy. So Janskis have units of watts per meter squared per hertz. So it's a specific flux or a specific usually call it like this, FU. So a bright radio source, for instance, is 1 Jansky. So we're talking about 1 million Janskis per steradian, but that's a pretty big part of the sky, right? That's 1/12 of the sky. Okay, so people have sort of turned this crank for a while now, and observations are getting better and better over time, but it allows us to get a measurement of the angular diameter distance, a function of redshift, and these are cosmological curves, right? One's omega matter equals 0, one's omega matter equals 0.3, and no lambda term, and one has a lambda term in it. It's not very good. The data's still pretty ratty, but it's kind of nice that it's consistent with the supernova data, because it really doesn't make any appeal to the same sorts of physics that supernovae make an appeal to, right? Nor is it directly related to the way in which we do physics with the cosmic background radiation. Remember that power spectrum that I showed you that had extra power on sort of 1-degree scales? That was due to us basically making measurements of the D sound, the sort of size scale of the sound waves as they propagated from the beginning of time to the time of recombination. So it's yet another way of making this measurement. What's also interesting, of course, is that we can just look at large maps of the cosmic background radiation and just essentially look for holes. And how do we know that those holes aren't just part of the CMB itself? It's because there's a very specific spectral signature of what we expect to see. So the CMB is just going to have slightly different temperatures. So the hole, if I have a slightly higher temperature, a slightly lower temperature, I'm just moving this dash curve around. But the Sinyaev-Seldovich effect will actually add this really sort of strange structure onto the spectrum of the CMB. So it means we make measurements at multiple different frequencies, and we can infer where there are actually clusters on the sky. And you can do this, this is actually quite interesting. You can find clusters without having to take optical images of the sky. Right? The way that people have traditionally been finding clusters is with optical images, and then more recently people have been using sort of all-sky X-ray survey campaigns to find these things, right? Because if there are clusters, they're going to be bright in X-rays. Except both of those wind up going, sort of the effect winds up going down by 1 over r squared, right? Because if we're trying to figure out the luminosity of an X-ray source, obviously, as I go farther and farther away, like to redshift 1, redshift 2, it becomes very hard to find some sort of emitting X-ray blob, right? Likewise, the galaxies just get fainter. However, again, if I look at the Sinyaev-Seldovich effect, there's nothing over there on that equation that says delta temperature divided by temperature should have some sort of distance, as in from us to that source, associated with it. So independent of the distance of that cluster to us, we should see a temperature decrement. And one of the things that people are trying to do, in particular some of the physics professors here at Berkeley, is to do a wide field campaign at microwave wave bands to find clusters. Not just to do Sinyaev-Seldovich, because then you need X-ray, But if you can find clusters, you can basically count up the number of clusters as a function of redshift, because then you wind up doing some follow-up and you get the redshifts of those clusters that you do find. And what you notice is that the number of clusters, this is the number of clusters per unit redshift, out to redshift of about 2, is highly dependent upon the cosmology that we live in, right? If I add omega matter, a little bit more matter in the universe, I wind up getting more clusters. If I crank it down, I get less clusters. And so what they're hoping to do, this is just a simulation, what they're hoping to do is basically just count clusters. And counting clusters is yet another way of getting at the cosmology. Okay, any questions about that? All right. So I want to talk now about structure and structure formation, the origin of structure. This is not what I want to talk about. One of the things to recognize, I think this came up in a question that somebody had last time, is that in a matter-dominated universe, which we said was kind of an appropriate regime to be in when we talked about the universe at the time of recombination, the density of matter goes like r to the minus 3. You know that already. Which is temperature to the minus 3. So as, temperature to the plus 3. So as I wind up decreasing the temperature, I wind up effectively, because we know there's an inverse relationship between R and T, I wind up effectively also decreasing you could think of it as a mass density, but it could also be the energy density of matter. Okay, so now if I want to know what some sort of perturbation is, delta P is, delta rho, this is 3T times T squared times whatever perturbation I have in temperature. Again, this is in a matter-dominated universe. So if I want to know what delta rho divided by rho is, that's just 3T squared delta T divided by T cubed. And this is just 3 delta T divided by T. Remember, at the time of recombination, this is true at all redshifts, but at the time of recombination, this is something I can actually measure from the cosmic background radiation. We said at the beginning of class, or we said at the end of last class, this is 3 times 10 to the minus 5. So 3 times 3, as you've learned in this class, is 10. So delta rho divided by rho is basically 10 to the minus 4. So at the time of recombination, our measurements of the CMB, looking at changes of the temperature in different patches of the sky, tell us that the typical sort of changes of density of matter in different patches of the sky, first of all, is linearly related to that temperature, right? So if I have a slightly higher temperature, it's also associated with a slightly higher mass density. But we know that those changes are there at 10 to the minus 4, right? And we talked about also at the very end of class last time that the sort of delta rho divided by rho today, so if you think of rho now as sort of the average mass density of the universe, this is something comparable of order the critical density. And then we look around us and we try to figure out what this is. This is of order 10 to the 29. So we have regions of space that are much, much higher density than the other regions of space around us, the average region of space. But that was much, much smaller, right? So going from here to here is in many ways what most of this class in 7A was about, right? It was about structure formation. It was about star formation. It was how do we get to where we are today. And clearly there had to be a lot that happened from a redshift of 1100 to a redshift of 0 to get to this point. turns out that on small scales, gravity is nice and nonlinear, and it just sort of pulls everything in. So once you start building up big enough structures that are dense enough, and this density enhancement winds up growing, as we'll see in a second, over time, then sort of gravity takes over, and then you wind up getting these very, very large structures, very large overdensities. Okay, so let me talk just for a second about the growth of structure and think about how these perturbations wind up growing. So think now about this early universe. Think about the time of recombination, and the photons are saying goodbye to the ordinary matter, to the baryons. And before that, they were coupled in this sort of ionized soup. Now the photons free stream out, and now the mass is saying, oh, look, I'm in an overdense region. I'm going to be very happy to collapse or start my collapse process, right? So you might think of this in a very cartoonish way of having some average density of the universe, and then you have some other patch in some other part of the universe that has some other density. And we'll just say that rho prime is greater than rho. We want to know how this number winds up growing relative to this number. What's happening in this universe? So this is our flat universe. Think about this in a metric sense, and let's assume that I'm talking about very, very large scales. What's happening at a later time to this whole picture? Yeah, the whole thing is expanding, right? So clearly, in absolute terms, rho prime and rho, for a while, are actually both going down, right? Because this whole thing is expanding. We have a certain amount of matter here, a certain amount of matter here, and if we confine ourselves to be within this circle, then that's going to wind up being true. First of all, does it make sense for mass to flow out of this circle and into the average part of the universe? I see some shaking heads. Pauline, one.
No, because we already said that matter has a zero pressure, so it's not like the bits inside are going to
Yeah, and if anything, something which is on the interface right outside of this circle is going to say, ooh, there's a lot more matter over here than there is over here. I'm going to flow inward, right? So if anything, this rho prime for all of t is going to be greater than rho. And the way we think about this is that each patch of rho prime will develop independent of the rest of the universe. It's as if it's got its own sort of universe here, which is deciding whether it's going to expand or collapse based on how much matter it has. In the rho prime frame region, we're going to have some h prime squared, Hubble constant squared, r minus 8 pi 3 g rho prime r squared is equal to minus kc squared. Again, we're just assuming this is matter dominated. And likewise, in the rho frame, we're going to have some h squared r squared minus 8 pi over 3 g rho r squared minus kc squared. Now, in principle, these r's are going to be slightly different than each other, and that's sort of the thing that we want to see how they scale with r. But everyone agrees that if I have a different density, the dynamics of the universe in this local patch is going to be slightly different than the dynamics of the universe in that patch right there. So when we talk about delta rho divided by rho, so we want to see now how this perturbation grows. This is rho prime minus rho divided by rho. And we can plug this in here. We get 3 kc squared divided by 8 pi g rho r squared. And in in a radiation-dominated universe, now if we want to put in not matter, but we want to put in just sort of radiation, we know that rho of t is going to go like r to the minus 4. So r is going to go like t to the 1/2. We showed that before. This is radiation-dominated. And in matter-dominated, rho of t goes like r to the minus 3. So what you notice here is that I have rho times r squared. And so if I want to see how rho times r squared goes in a radiation-dominated universe, this goes like 1 over r squared. So this goes like 1 over t. So I can plug in for this quantity right here and see how these different perturbations grow with time. So in a radiation-dominated universe, these perturbations, delta rho divided by rho, are going to equal some delta rho divided by rho initial, t divided by t initial. Just grows linearly. In a matter-dominated universe, I get a similar thing, which is delta rho divided by rho initial, t divided by t initial to the 2/3 power. All of this to say is that in both a radiation-dominated and a matter-dominated universe, if I have a perturbation at some time t initial, which we could call time recombination if we're thinking about a matter-dominated universe after recombination, we want to see how those perturbations grow. We now know that in a sense, we can think of this just in a cosmological way of this rho prime region separating away from this rho region and sort of doing its own thing. And that enhancement is going to wind up growing in time, right? So if I start off at something like 300,000 years after the Big Bang, and I play the movie forward by another order of magnitude in time, I can wind up calculating now what the density enhancement is. Eventually, you get to density enhancements of order unity, and then gravity becomes truly nonlinear, and you wind up sort of breaking away from this cosmological way of thinking about structure formation to all the sort of gastrophysics stuff that we've been worrying about throughout this course. Yes?
In a radiation-dominated universe, the particles are massless. Why do they still form?
Well, so if there's an overdensity, if you just had radiation, right, and you didn't have matter, you would have hot spots and cold spots, right? Because you have perturbations from early times in the universe, and those perturbations wind up also growing from the early time of the universe. So if I start off with a tiny perturbation and the universe just it starts expanding and that perturbation grows, right, it can move as fast as c divided by square root of 3 in that plasma. And it doesn't matter whether it's pure energy or relativistic particles like electrons and protons. Sound travels at that very high speed through that space. So even though the universe is expanding, these perturbations wind up growing. So you wind up getting large patches. Well, these aren't that big physically, but they're large enough patches that you can wind up sort of staying hot and staying cold. And if you want to think about hot and cold in the context of a little bit more energy density here and a little less energy density there, which is fine, you can just divide that by c squared, and there you've got your matter equivalent density, right? So we're basically making an appeal to what dominates the universe at that time, and here we think of this as the matter density equivalent of the radiation, right? So just to make it clear, I'm talking about in a radiation-dominated universe. What do I talk about when I talk about rho? This is basically the energy density of the universe. Think of it as what we now think of as the black body, but it's related to the average temperature of the universe at that time, divided by c squared. And remember, this goes like t to the fourth power. So this is the reason why the radiation density is going down like r to the minus 4 and not r to the minus 3. Yes?
I was wondering, one of the things that I remember us saying when we first started cosmology was that gravitationally bound systems don't expand. It's just the universe around them that expands.
Mm-hmm.
So I'm wondering, is there some like density where this whole discussion of like the whole discussion of expansion like breaks down?
Yeah, I think that's a very good question. Yeah, I don't know the exact number, right? Because obviously you have both processes happening at the same time. But I always think of this, once this gets to order unity, then the density here is, the perturbations here are effectively a factor of 2 larger than they are over here, right? And pretty quickly after that, you get into a nonlinear regime where you just stop thinking about the cosmology aspect of that. And you start thinking about, oh, now this gas is basically bound to itself. Let's figure out what happens to it. Now, that's not exactly true because it doesn't, I didn't give you the size scale of this. This could be 100 megaparsecs, or it could be, 10 kiloparsecs. I didn't give you this size scale. So you have to come up with this, sort of statement about whether this perturbation is large enough to actually form these structures. But eventually you're going to wind up talking about a gene's mass, right, and a gene's length. And it's once you start saying, am I satisfying the gene's criterion, that's kind of when you stop really thinking about how cosmology is going to drive these perturbations. Because as soon as I get over the gene's criterion, remember, because this stuff is also going to start cooling, right, on its own. It's going to have internal processes like line cooling, 21 centimeter cooling. And it's going to do a lot of stuff to try to get rid of its heat. It's also going to be receiving heat from other parts of the universe, but it's going to be sort of doing the astrophysics and the stuff that this gas does to try to collapse, right? But once you get to this density, delta rho divided by rho of 1, then all that stuff becomes a big consideration. But until then, we think of this as essentially being driven by the cosmology and just the expansion of the universe. Let me now show you how this structure grows and actually doesn't grow at early times. If I look at ourselves at very, very early times, 1 second after the Big Bang, we know that dark matter and normal matter are not in equal proportion to each other in terms of the density, right? So dark matter dominates, you know that already. Normal matter, as we'll see in about 15 minutes from now, is sort of all starting to be created around 1 second, and from 1 second to about 1,000 seconds, all the baryons in the universe are created. So this is an appropriate time to look at. But what do we know about normal matter? This normal matter is highly coupled to the photons, and the photons are hot, right? So this is why we have this plasma. If I have slightly higher density of matter, I'm going to be a little bit hotter, and I'm going to essentially wash those perturbations out. Any perturbations that are there, gravitational perturbations in this very early time in the universe, however, might not be felt by the normal matter, but the dark matter says, I don't care what you say to me, radiation. I'm going to do whatever I want. And the dark matter is quite happy to follow along this perturbation, which basically grows linearly with time in this early history of the universe. So as I get to 1,000 years after the Big Bang, any initial inhomogeneities in the overall temperature of the universe, right? Because at that time, you're just not even talking about matter at very, very early times. You're just talking about energy density. Any of those inhomogeneities wind up being felt by and sort of magnified by the dark matter. And yet, look what happens to the normal matter. The normal matter would love to flow into these overdensities where the dark matter is, but the photons say, no, you are not allowed to do that. They start flowing in, and then they wind up getting hotter. It produces more photons, which basically transports the heat out of that perturbation. But the dark matter is quite happy to do this. So at the time of recombination, what happens is the dark matter has grown its perturbations as large as it wants to be, as large as it can. And all of a sudden, the ordinary matter decouples from the photons. It says, oh, there's a big potential well over there. I'm going to go there. Right? The structure in the universe that we have today wouldn't be nearly as nonlinear as it is without the presence of dark matter. You actually need, in the universe that we live in, some matter which is capable of being essentially decoupled from radiation very early on. And if it's not, those perturbations don't grow as fast as they do now. And this leads us to the last sort of cosmic ruler that I'll talk about, and this is what's called baryon oscillations. So here is basically a depiction of a perturbation propagating out through cosmological time. And remember, what we talked about is that there's a particular scale of at time of recombination. I don't know why this should be kiloparsecs. This should be 200 megaparsecs. I'm going to kill that. Sorry. So the size scale at the time of recombination of these perturbations, which gives us some sort of typical length right here, is 0.2 megaparsecs. But it's not just one perturbation, it's lots of perturbations. So this is the idea of the rain sort of trickling down onto the pond and then stopping the movie at some later time and figuring out what the typical distances to all these different peaks and troughs are. It washes this whole thing out and you get this 1% effect. The point is that at the time of recombination, photons decouple from matter, and all of a sudden there are these perturbations whose densities are sort of delta rho divided by rho of 10 to the minus 4. And those density enhancements wind up growing and growing and growing. But before that time, they were all really coupled with each other. So if I have a perturbation, the perturbation has to travel along with the rest of the universe. So let me just explain what's happening right here. This is quite complicated. Here are our perturbations as a function of time, and we're playing the movie forward from basically the Big Bang up to a redshift of 10. And what you wind up seeing is that these perturbations wind up growing as a function of time, and follow the blue curve for now. And the blue curve, obviously, and the black curve, which is dark matter, are quite closely connected with each other because they're basically falling into each other, right? They're producing these perturbations mutually for each other. And look at the density enhancement of now the photons and the neutrinos. Those get washed out over time, right? Because you just have these relativistic particles which are just free streaming out and sort of taking themselves out of, just basically getting themselves into a very happy state where they're not actually clumped up in one region of space. All right, so what are we looking at here? We're basically dropping this petal into this pond, and everything's traveling together at early times, except dark matter says, nah, I'm just going to do my own thing, and it travels out. Until that time, the photons and the matter are highly coupled with each other. So look at the blue curve and the red curve at the very beginning. Blue curve and red curve are right on top of each other. And then matter decouples, boom. Right, so the photons free stream out, and the matter is now feeling this perturbation that was actually there before because of the dark matter. what does that mean? all of this, right? This is just a simulation, of course, looking at one perturbation in a sort of expanding universe. What this means is that the Big Bang had these perturbations that left this imprint of some size scale at the time of recombination of something of order 0.2 megaparsecs. And that is the origin of this bump that we see in the CMB spectrum at about 1 degree. Okay? However, those perturbations wind up continuing to grow. So the universe basically leaves this imprint of this sort of very specialized scale, and then the universe winds up growing from there. And so you wind up sort of having this sort of typical scale when the universe is small, and then the universe winds up expanding. And what it means is that if I have a hot spot in the CMB over here, all I have to do is walk by 0.2 megaparsecs at the time of recombination, and I'm much more probable of having a hot spot. Now, if I have a galaxy cluster right here at later times, that galaxy cluster probably formed because I had density enhancements earlier on, right? Now all I have to do is walk a distance, a preferential distance, in this case at redshift of 10, it would be of 150 megaparsecs because the size scale has grown. And I have a higher probability of finding a galaxy cluster. So that means that if I look off at the universe and I count galaxies, and I count the locations of where those galaxies are, the imprint of the Big Bang is actually left in the distribution of those galaxies. This is what's called baryon oscillations. It's a kind of a weird name, but it's basically saying that I have imprints of density enhancements which wind up basically growing, and those relics are observed today. Remember how we talked about when we introduced cosmology the idea that the universe was homogeneous and isotropic? And I said this was true on sort of 100 megaparsec scales? It turns out that that's not exactly true. It turns out that if I stand somewhere in the universe and I walk by 150 megaparsecs, I have a higher probability of being on top of another galaxy cluster. And if I go another 150 megaparsecs, I have another higher probability of being on top of a galaxy cluster. And by counting the number of galaxies as a function of distance, this is what's called a correlation function, you can get a very good constraint on omega matter times the Hubble constant squared. But think about that. And this is one of the great results from the Sloan Digital Sky Survey, where they saw a density enhancement on these scales right here. And this is, at this case, a redshift of a sort of typical redshift of 0.3. And so that little bump right there is telling us that our assumption that the universe is homogeneous on 100 megaparsec scales is actually wrong. There's actually a little bit of extra power there. And by doing this as a function of redshift, now you can map out how that sort of typical size scale will wind up changing as a function of cosmic time. And people are hoping, and this is a simulation for the future with something called the Large Synoptic Survey Telescope, to see these wiggles, because it's now not just the initial perturbation, it's harmonics of that perturbation, and see that imprint on galaxies and sort of galaxy distributions. So this is really cool, and this is kind of a new direction in cosmology. One of these fundamental questions that we have, of course, so any questions about that? One of the fundamental questions we have is, where did these perturbations come from in the beginning, right? Remember I said that there is this sort of hand-wavy statement about there being more perturbations that are small relative to the perturbations that are large. Well, they're all around of order 10 to the minus 4 in density units at the time of recombination. But it's not clear how they got there in the first place. And if you sort of invoke a universe that has, say, quantum fluctuations at the time of the Big Bang, where you have slightly higher density and slightly lower density just because quantum mechanics says it can't be perfectly uniform, on the very, very tiniest scales, on the Planck scale, you can imagine if I start off with a total amount of energy at the time of the Big Bang, right, epsilon after T0, I wind up having some high energy density. If the universe is totally uniform at that time, then the universe winds up expanding and cooling, and it's completely boring because there aren't any density inhomogeneities. We need a 10 to the minus 4 density inhomogeneity 300,000 years after the Big Bang. And so it's unclear how to do this from sort of a standard picture of a Big Bang. Instead, what people like to invoke is this idea that quantum fluctuations, which were there at sort of the very, very moments of the creation of space-time, got amplified. So the Planck length essentially got amplified to large enough scales that they could be observable on cosmological scales at times of 300,000 years after the Big Bang. So you have to go from Planck scales, I forget the number, 10 to the minus 34 meters or something, to something of order, a megaparsec over the time of just 300,000 years. And if you just do the numbers and you sort of play the movie backwards from a radiation-dominated universe and you ask what the scale size of the universe was, it didn't change by enough to make those perturbations, those quantum perturbations, large enough to become macroscopic. And this is one of the many reasons that people have invoked the need for something called inflation. The idea that you have perturbations at early times in the universe, which are very tiny, but then the universe says, I'm going to expand exponentially for the next 10 to the minus 34 seconds, and then I'm going to be much larger than I would have been if I just didn't have this inflationary period. And this sounds like major hocus pocus, right? And it kind of is hocus pocus, but that's okay. We've been doing a lot of hocus pocus in this class. You're all used to that. Inflation, though, yes?
But what would cause this inflation?
I'll get to that in 18 minutes. The shorter answer is, hey, what causes the cosmological constant not to be 0? Right, good answer. I'll sort of end with some speculation about what it may be, but we think it happens. Let's put it that way. Okay, so we sort of like the idea of an inflationary period because it magnifies the quantum fluctuations that are very easy to make, and you don't have to sort of add new physics to just add quantum fluctuations on Planck scales. Inflation, and this is really just talking about how there's a moment in the history of the universe where R grows exponentially. To magnify quantum fluctuations. Is more important, actually, in solving some of these other cosmological problems that kind of crop up when you think about a standard Big Bang without inflation. And there are really 3 of them. One is the so-called horizon problem. This is different from the Verizon problem that many of you are having. Sorry, I'm just trying out new jokes. There's the so-called flatness problem. And there's one called the no magnetic monopole problem. I don't know it. Oh. Oh yeah. Okay, you ready? It's really, really geeky, and it just hit me. Right, that. So think of Compton upscattering as the effect of extra credit on the grade distribution. So this is the grade distribution as it would be before you guys do extra credit, and then you'll all get bumped up by a little bit. Are you just trying to stall so that I don't have to talk about all the stuff that happens, baryogenesis and stuff? No, you're right. I Okay, where was I? Hello. Ah! Go away. Okay. Yeah, I figured that out like 2 years ago. If you project black, you don't have to turn off your screen each time. So horizon problem, flatness problem, what I'll focus on now. We've talked a little bit about the flatness problem. Remember when we derived what omega of z was as a function of omega naught? There was some function of redshift. And we said that if omega naught is exactly 1 today, then it was always 1. So we're always at the critical density. Another way to think about it is sort of the opposite of that. And so I'll just recouch what you guys derived already. 1 over omega naught minus 1 is equal to 1 over omega minus 1 times 1 plus z. This is a recouching of this problem that we did before when we were talking about a matter-dominated universe. This is kind of the flatness problem captured in a strange way. It says that if omega at some time wasn't exactly 1 at some higher redshift, then today omega would be vastly different from 1 now, right? So it's kind of the opposite of, or it's kind of a different way of viewing this problem. This is a problem because it turns out that if omega at the time of recombination was 0.009, this is 1.009, then omega today would be 50. So if you have a slightly different universe that's slightly different from flat at early times, today it gets completely magnified. So a tiny change here gets magnified today, which means that the universe had to be really flat at early times just for us to get something which isn't exactly 1 today, or something which is close to 1 today. So the flatness problem is solved by inflation by taking a universe which may or may not be flat, right? So it's got some omega effectively right after the Big Bang, which can be anything it wants. And then you make it so large that you wind up looking at a structure, you wind up looking at in our sort of local volume of the universe, this is now our Hubble, this is our horizon, which we can figure out by knowing the Hubble's constant and knowing the other cosmological parameters. We look inside of that and we say it's very nearly flat, right? So it's taking this soccer ball, which is completely, I should have brought a soccer ball. Here's a soccer ball, and it's not flat at all, right? Topologically, it's not flat. Now make this soccer ball larger by a factor of 10 to the 29, so make it a megaparsec size, and now look at the surface of this soccer ball. Does it look flat to you? Yeah. So what inflation does is it says universe can be any sort of shape and topology it wants at early times. If I just make it really big, everyone who lives inside of a small volume of that will wind up seeing the shape be almost exactly flat. So what inflation predicts is that when people get better and better at measuring omega total, they're basically going to be measuring 1. Right? If it's different than that by enough, then that's going to have some major implications for most types of inflation. So that's one thing. That's how the flatness problem is solved by inflation. The other is the so-called horizon problem. The idea here that here we are looking off at the CMB, and it has the temperature of the CMB of whatever, and we look off to the other side, and it has the temperature of the CMB. From here to here, we are causally connected because there's been enough time in the history of the universe for the CMB photons to get to us from over there and to get to us from over here. But from this distance to this distance, the part of the sky over there and the part of the sky over there are not actually talking to each other. So how do they know to be exactly the same temperature? How is it that some part of the universe didn't say, "Oh, I'm gonna grow my perturbations at earlier times, and I'm gonna just be 3 degrees Kelvin today"? And how does it know over there that it's also going to be 3 degrees Kelvin? When you look out at the CMB, even though we talked about these non-uniformities at the sort of few times 10 to the minus 5 level in temperature, it's tremendously homogeneous, right, at the time of recombination. And that's troublesome because we now know that those things were never actually causally connected if we just invoke a standard Big Bang cosmology. The way that inflation helps this problem is it winds up having the universe be essentially much smaller at very, very early times. It allows there to be enough time in the history of the universe for there to be really sort of a washing out of all these different changes which may or may not be there sort of before 10 to the minus 35 seconds or so. And so big changes, which would have gotten magnified to very large differences in temperature as we would view it today, have some time to sort of work themselves out. That is, most of the universe that we see over there and over there, all of that was actually causally connected at some point. So the reason why they have the same temperature is that they were close enough and there was enough time for essentially information to transfer back and forth. So we had this sort of small ball, if you want to think about it, of plasma. And then the universe grew to very large sizes, and now we look off at this and we say, of course they're the same temperature. Because at early times, they were in equilibrium with each other. So that's how the horizon problem is solved. And this other magnetic monopole thing, there's sort of theories that describe the grand unification of the electroweak theory, the strong and the strong force and the electroweak force. And those wind up predicting that there should be essentially magnets out there which have only a north pole or only a south pole. That's what's a magnetic monopole. In the context of an electron, you can have essentially a single point, and you have your field lines moving out from there. There's predictions that you should have plenty of essentially the equivalent in a magnetic sense of some sort of magnetic monopole and field lines only moving outward and not bending back on itself. And we don't see any of these around in the laboratory, right? And there's no evidence that these things exist. The idea is that these magnetic monopoles were indeed created at very, very early times, but then the universe got really, really big, so the probability of them actually being within our horizon is really small. This seems very hand-wavy, but the whole point is you need to have the universe at early times be causally connected to itself, and large regions of the universe today have to be causally connected. We have to solve this flatness problem, and we have to solve the horizon problem. And the magnetic monopole thing is just saying that the volume of the universe got much larger, so we've basically gotten rid of we've basically removed magnetic monopoles from our observable horizon. So this idea of inflation was proposed in the early 80s. Linde and Guth are sort of credited with some of the early development of this. And how, yeah, I know, I think Linde also looks really scary. If you see him on the BART, you should get out of the car. So this is the standard theory, right? If we think about a radiation-dominated universe at early times, and then it just winds up growing, it goes like t to the 1/2, and then it winds up changing the way it scales as we get to later times. But 10 to the minus 40 seconds after the Big Bang or thereabouts, we invoke this big inflationary period where the universe got bigger the R grew by a factor of 10 to the 28 or something. And so the volume of the universe got bigger by of order like 10 to the 90 in a very, very short amount of time. So where did this come from? I have no idea. But we can talk about that a little bit. I want to talk just for about 10 minutes or so about the buildup of ordinary matter in the universe. And it should be pretty clear now and you'll see this in your review and also in the section if you go to it on Friday and on Monday, a sort of outline of the different times in the early history of the universe. But I wanted to focus not so much on the really early times now. I wanted to just skip ahead to discussion of particles and how we wind up having particles in the universe. Think about this. We have a temperature, right? This temperature is incredibly hot at early times. And again, without having to do all this inflation stuff, we can say that kT divided by 1.3 mega electron volts goes like 1 over 10 to the 1/2 power. That is to say, at 1 second in the universe, after the Big Bang, the average temperature of the universe is 1.3 mega electron volts. This is obviously an energy, not a temperature. But what's the sort of typical energies that you associate with, say, an electron? Does anyone remember what the rest mass equivalent energy is of an electron? MEC squared. 511 kilo electron volts. So at earlier times, the universe was so hot that we were capable of taking two photons, which had tremendous energy, and they could smash into each other and then pair produce. Right? Likewise, those electrons could wind up smashing into each other and then produce photons. This is why we have this concept of a particle soup. And what you see is that at early times, as the temperature is cooling, every time you get to a temperature which is sort of comparable to the rest mass energy of that particle, those particles that are created all of a sudden have a very hard time in smashing into each other and making photons that have a similar temperature. Likewise, after that time, I don't have many photons of high enough energy to produce those particles anymore in this process right here. So one of the very strange things, and we don't have a great answer for this, is that if you think about these two processes when the temperature is high, when the temperature is higher than the rest mass energy of one of these particles, this now doesn't have to just be an electron. It could be a muon, it could be a neutrino, it could be anything. As the temperature is higher than this, you sort of freely go back and forth between particle and antiparticle and photons. But as you wind up cooling down, what's very strange is that we don't have zero of those particles left over, right? There should have been this symmetry between these particles in the total numbers of them. And what we have in our universe is more electrons than anti-electrons. And this is what's called symmetry breaking. And it's not clear at all why there is symmetry breaking, but it says there's something very fundamental about this process of annihilating two photons and producing two particles. You have a slightly higher probability at a very tiny level of producing more of one kind than more of the other. Or another way to think about it is that if you smash these two together, every now and then you wind up not actually getting that process going in exactly the same rate as you get this process. So this is strange, but we live in a universe that has matter. Of course, if we lived in a universe that had antimatter, we'd call what we call today matter antimatter. But, so there's a symmetry there, but there's an asymmetry in the way that the universe likes to create this stuff. Anyway, so the universe cools. All of a sudden, we can get electrons, and we still certainly do have some positrons around. But we're also now making elementary particles not elementary particles anymore, like muons and neutrinos, but now we can make larger things out of quarks. We can start making baryons, right? And baryons can form, what's the typical mass of, say, a proton relative to an electron? Yeah, 1,000 times. So 1,800 times MEC squared. So 2,000 times that is what? What? It's a lot. So this is 0.5 MeV. We'll multiply this by 2. Yeah. So what is it? Yeah, so it's 1 giga-electron volt. Right? It's 10 to the 9. This is almost 10 to the 6. This is almost 10 to the 9. Yeah. So when the universe is about that temperature, right, and we can just figure out what time that was just by taking the square root, basically, we wind up getting the formation of baryons. Now, remember that we said that in the universe we wind up producing not just protons and neutrons, but we also wind up producing helium. And this whole process is called primordial nucleosynthesis. We wind up having a proton and neutron, which wind up merging, releasing a little bit of energy. That's left with a deuteron. We have another one of these deuterons coming together, producing a helium-3, and then we wind up getting another neutron to get helium-4. This is the process that happens, and that gets us to helium-4. And this happens at a temperature of something like 1 billion degrees Kelvin. One of the things that's important to understand is that it's pretty easy just from looking at this pair production thing and the fact that temperature is cooling down in the universe to get neutrons and protons. What's not so obvious is that neutrons, free neutrons, that is ones that aren't bound in a nucleus, for whatever reason, actually decay on sort of 1,000-second timescales. So if I have a free neutron and it's not part of a nucleus, it just decays, right? This means that if I don't start binding up these neutrons that I just created at whatever time is associated with 1 giga-electron volt, then the neutrons disappear and then I don't get matter. The other thing is I better basically get to the point where I cool down enough that I can have deuterium sitting around for long enough that I can smash 2 deuterium atoms together. So you have a very small region of time in the history of the universe where you can produce the atoms that we wind up having at the end of the Big Bang. And from 1 second up to 1,000 seconds, what you see, let's look at the free neutrons. This is this black line here. Here's the free neutrons relative to the protons. And you wind up seeing that after about 1,000 seconds, they wind up just decaying down. There's just fewer and fewer of them. However, we have to wait until what's called the deuterium bottleneck to be satisfied, where we make enough deuterium that all of a sudden we can start making lots of helium. And once we start making helium, then we can start doing a little bit more and start making beryllium and lithium and stuff like that. But you see that there's a tiny, tiny region in the history of the universe where I make beryllium. And after that, there's no more time left because the universe is cooled and it's also expanded dramatically. And so the densities are low, and so you don't wind up getting these nucleosynthetic processes happening. One of the great triumphs of the Big Bang theory as a whole is that it makes predictions about nucleosynthesis. It makes predictions about the ratios that we should wind up expecting for different of these different atoms in nature. And people are able to now look at spectra of quasars, and they can figure out the ratio of deuterium to hydrogen, right? So that's this red line. And these are the relative strengths, and what's observed are these quantities right up here. We can, of course, do hydrogen relative to helium, right? Because we can just look at abundances of clouds. But we can also now do this with lithium and helium-3, et cetera. And these are all the observations of all these different abundances. And you see that, obviously you get much less helium, but you can certainly get much less deuterium and even less lithium, down by almost 1 billion times from the abundances of hydrogen. And then you look at a megabaryon times the Hubble constant, and this is what the prediction should be based on our observations of these two quantities today. And what you notice is that they all wind up lining up with the observations. This is one of the ways I said at the very, very beginning when we're talking about black holes, not very beginning. In the middle, we talked about black holes as possible dark matter candidates. And we said, well, the problem with that is that we actually can more or less account for all the baryons in the universe based on our observations of what we can make today. That is, we can look at all the baryons, and they're in the right proportion today as they were at the very beginning of time for these various theories. So this is a great triumph. And it sort of certainly says that we live in a pretty special universe where all these different things had to come together. We had to overcome the deuterium bottleneck, for instance. If we had lived in a different universe where there had been slightly different parameters, people have started thinking about this and wondering what would happen. So you can actually make plots of this fine structure constant versus the strong coupling constant. So you can look at fundamental parameters of what binds things together. And what you notice is that we happen to live in a pretty special space where if the universe had slightly different values from what they are observed to be today, then there'd be these places where we wouldn't have a universe like we have today. We wouldn't have carbon in this yellow area. We wouldn't have compact objects like neutron stars and white dwarfs. And here, this diproton disaster would actually allow basically a helium atom to have no neutrons. So you would allow yourself to have basically 2 protons in an atom, and there then would be a very, very quick conduit to burning up all of the hydrogen into this diproton stuff in stars, so we wouldn't have stars around today. We have to live in this white area for us to actually observe that we live in this white area. And then likewise, you can do some other stuff by changing the mass of the electron versus the mass of the proton, also as a function of the fine structure constant. And you also wind up seeing that we live in a reasonably special space. So this is interesting. We do live in a very special space. We don't understand the origin of inflation. We don't understand the origin of the cosmological constant. And what you wind up seeing is that if you start thinking of this as some sort of vacuum energy that is associated with the energy associated with the Planck scales, there's something really wrong with that idea. The energy density associated with dark matter is just c squared rho of lambda, and this is c squared critical density today times omega of lambda today, and this number is 6.22 times 10 to the minus 10 joules per meter cubed. If we associate an energy with the Planck scale, so we basically have a Planck energy divided by Planck length cubed, that number is 10 to the 114 joules per meter cubed. These numbers are different by 10 to the 120. If we think of dark energy, and perhaps even the thing that drives inflation, as being related to the vacuum, our concept of what the vacuum energy density should be is way, way off. Why this should be down by 10 to the 20 orders of magnitude is a complete mystery. So there's certainly a great deal to do in cosmology, but I hope what you've seen in this course is that there's a great deal to do and understand basically in all aspects of astrophysics. And I think you've gotten a good feeling, even though I told you that 3 times 3 is 10, that there's a great deal of precision of what we do, and our understanding of the universe, I think, is pretty remarkable. So I encourage you all to continue on in astrophysics, and in physics for that matter. That's okay too. And to try to start doing some research. You know, we're touching on many, many topics in the 7A, 7B series. It gets deeper and deeper, but what you'll find, if you haven't seen this already in your own work, is that we really don't understand a tremendous amount about the universe. And I think that's fantastically exciting about this field. So I'll end with that, and I'll ask you guys, those that didn't fill out a form in Jonathan's section for this class, please do. And I think in Yuk Yun's section, you only filled out an evaluation form for the section itself and not this class. So we'll pass this around, And then I'll ask somebody to volunteer to bring this up to Dexter Stewart. It should only take you a couple minutes. Will you do it? Here, you can just pass these around. Oh, it does go to Raina now? Okay, so she's in the front office.